Welcome to Alaska Earthquake Science Facts. I'm Carl Tape. Alaska's environment, wind, rivers, permafrost, glaciers, sea ice, can be monitored using the faint signals of continuously moving ground recorded by seismometers. This video is all about the background needed for that fact. To really dive in, I encourage you to go to the next video in this sequence. Here's a photo of Dr. Kyle Smith, UAF PhD student, installing a seismometer at station F6TP in Minto Flats, Central Alaska. This particular seismometer recorded continuously in the ground, this hole shown here, for 4 years. This fact is about some of the amazing and ordinary things that an amazing instrument can record. Here are 3 themes. They're actually the takeaway points for this Part A section. A seismometer can record signals coming from all distances. 2, the Earth is continuously in motion. 3, the frequency domain offers a powerful tool for analyzing signals of ground motion. And I'll put at the bottom, is this really a topic that can be discussed at a casual social gathering, which is one of the criteria for making these facts? And can it be done in a couple minutes? Well, I encourage you to try it. I can't do it myself, and I had to split this into 2 parts, A being the background, B being the fact, but still hopefully you find it a fascinating topic. Here's 25 seconds of ground motion recorded in Minto Flats, Central Alaska. So time is on the x-axis and velocity in microns per second is on the y-axis. If you note, this ground motion could be displacement, could be velocity or speed, or it could be acceleration. Seismometer captures all of these. They can be converted from one to the other. So let's take a look, microns per second for a moment. You know, it's a speed. So how fast is 1 micron per second? Let's put it into units like miles per hour. So micron per second, we can convert this through unit conversion, 10 to the 6 microns in a meter, 1,600 meters in a mile, and we get 0.0000022 miles per hour. So maybe the takeaway is that seismometers can record extremely low-level ground motions. It can detect a lot of different signals or noise, however you want to describe it. Back to the signal. So what are we looking at here? How would we describe this? Well, the first thing we might say is there's some spiky stuff going on. Pretty odd. There's also, if you look closely, there's kind of an oscillating pattern. So the first one is this spiking signal between about time 4, time 15 seconds. Then there's this oscillation with a period between peak to peak, that's the period, of about 6 seconds. And if we look at, this is looking at the acceleration instead of the velocity, but this is a remarkable signal. It's repeating, it looks very unusual. So we asked the question, what could this possibly be? And it turns out it's a moose. When we know that because we had cameras that were aiming at the seismometer, which is buried under this pile of sticks very close to where the moose is walking. And we have the recording of the moose walking over it. That's what you're seeing. And there's a really nice, if you search earthquake moose on YouTube, you can find a video put together by Helena Berman that aligns the moose walking, and every single one of these, about every half second, is one of her 4 feet hitting the ground. And this big step right here is the one where she almost steps right on the seismometer, which is buried under here. These sticks are actually put out there to try to prevent a large animal from wanting to step on it. So check that out if you really want to see this. And it starts us thinking about what seismometers are recording. Here's a new recording and a new type of signal. I would describe it as an abrupt signal that decays with time. So here's on the bottom, shows about 600 seconds, 10 minutes, where the signal comes in here at what we might call the noise level and then shoots up and just decays. So this is a different time period from that moose, but we can still sort of try to describe what kinds of things seismometers record. Let's zoom in on the first 25 seconds or so and look at what we would call as this noise. So here's 25 seconds again, similar to that duration of the moose signal. But we now have a new thing to add to our list of signals. First, in this second one, we didn't have any spiky repeating signal. We did have this oscillation, again, of about 5 or 6 seconds between this peak to peak. From here to here, it's about 5 or 6 seconds. So you can see this oscillation happening. We saw the abrupt signal that decays with time. And then there's a fourth one, which is this brushy signal. It's just a brushiness on top. And we'll get to this in the next video, but for here, we'll at least introduce where you can see it. So we can look at these four signals and just say what's being recorded in Minto Flats at this station. We've seen the spiky repeating signal. There's a moose. That's obviously not too common among all the signals being recorded, but we showed you at least one case where a moose was being recorded. There are lots of other animals, as it turns out. We'll get into these other ones. So turns out the other signal, the second one, was an earthquake recorded on the other side of the planet. So here we are on Minto Flats. And what this map is showing you is points that are equal distant from Minto Flats, F3. So all the points in here are 30 degrees away. All the points here are 90 degrees away, where you might think that if our station was at the North Pole, then the equator would be 90 degrees away, kind of like a latitude where this is your North Pole. Looks a little funny on this kind of projection, but what it means is there's a point on the Earth that is 180 degrees away. In other words, if you look straight down at your feet on the ground and just drilled a hole through the center of the Earth to the other side, it's called the Antipode, you would hit this point out here off Antarctica. That's as far as you could get from the station. So here it is, an earthquake that's something like 150 degrees, almost on the direct opposite side of the planet. And it's recorded in Central Alaska. We could go into the US Geological Survey site and dig up an event page that shows where this event is. We're being recorded up here. We can look at their page and 7.1 earthquake. It shows some interactive map. Not too much information. Did you feel it? There's no map. Felt report. Tell us about it. Citizen science. No one felt it. Magnitude 7.1. But hey, our seismometer felt it, and it was on the other side of the planet. The last signal is this high frequency, kind of brushy signal. And I'll just say, check out the next playlist video to see more. But before that, I will say as a hint, this is a view during the earthquake recording, December 4th, 2015. This is a view from the seismic station looking out, -18 Celsius. That's the Tanana River that's nearby the station, and that's snow. It's frozen. The river is frozen for many of the winter months, about a meter thick of ice. And when the moose was walking by, just to give you a comparison, this is what the scene looks like. It's one of the largest rivers in the interior, drains the Alaska Range and into the Yukon River. So the hint here is that the high frequency brushy signal is coming from the river. Okay, we now shift from looking at some signals of ground motion. We're going to discuss analyzing signals in the time domain and the frequency domain. We've been looking in the time domain. Recordings of how the ground moves as a function of time refers to the analysis of mathematical functions, signals, time series with respect to time. And then frequency domain, physics, electronics, engineering, stats. The frequency domain refers to the analysis of mathematical functions or signals with respect to frequency rather than time. That doesn't help us too much, so hopefully we'll get some good examples to fill us in. So some things in the world are best described by frequencies, and one of those is sound. Here's a picture of tuning forks. Probably most people have seen these. You can whack them and they'll vibrate at a certain frequency. They will emit a sound. You could put them, kind of hold them on a table, and it might resonate even louder. So they each make different sounds. You can see them labeled here, 512C. That's referring to the frequency. The cycles per second, 512 hertz is a C, and we have C, D, E, F, G, A, B, C. You can see the red ones I've labeled are octaves apart. They're both C notes, but you'll see that they're twice the frequency. A nice connection that octaves are apart by just doubling one frequency gives you the same note at a different octave. So here's sound. They're discrete frequencies, and they're best described, as you can see, as the labels on the tuning fork by the frequency of the sound. Piano, not too different. We look at the piano keys, and each key has a note, but in some sense, what defines that note is the sound that comes out of it when this hammer hits a string, or in a case of an electric piano, it's emitting a certain frequency. And so these are showing in hertz the frequency of each note on the piano. We can also think about a spectrum, a range of sound, and I'll show a few different examples of what you might find on the internet. This is showing human auditory fields. This shows in frequencies, humans have a capacity to hear from about 20 hertz to about 20,000 hertz. That's the range that we can pick up. We are not exceptional in the animal kingdom. There are creatures like elephants or moles that can hear lower sounds. There are cats and dogs that can hear higher frequencies, bats and dolphins even higher. And we'll see it's not just within the animal kingdom of what matters about the sound spectrum. There are a lot of practical purposes for using sounds. Here's another look at the sound spectrum, a little more wave-oriented version. We have the human's range of sound, again, from 20 hertz to about 20,000 hertz. We also see these depicted as these wavelengths, where the wavelength is getting shorter and shorter to the right at higher frequencies. Wavelength is the wave speed divided by the frequency. So at higher frequencies, if the wave speed is the same in a medium, higher frequencies are associated with shorter wavelengths. So if the frequency goes up, the wavelength goes down. So at high frequencies, we see short wavelengths. At low frequencies, long wavelengths. The speed of sound in air is about 340 meters per second. Speed of sound in water is about 1,480 meters per second, just to give you a reference. Another view of the sound spectrum in terms of applications, we have the infrasound, which is the lowest frequencies. Acoustic is referring to human acoustic range, what humans can hear. And then ultrasound is higher frequencies. So animals, chemistry, medical and destructive testing, diagnostic. Just to give you some numbers here, the 20 kilohertz would be 20,000 hertz, 2 megahertz would be 2 million hertz, 200 megahertz would be 200 million hertz. Interestingly, this comes up in a couple other science facts. We have with infrasound, this is low frequency sound waves. These are used for global monitoring of nuclear explosions and for scientific purposes such as characterizing volcanic eruptions. So we look at, in these earthquake science facts, infrasound comes up in a couple other places. It's good to see where it appears on the sound spectrum. Another thing described best by frequencies is light and color. And here's a spectacular example of color in nature. This happens to be taken from Wrangell St. Elias National Park, so good to have an Alaska connection. If we look at these rainbows, we see one rainbow here. We see another rainbow. You've all seen a secondary rainbow before. And the question is, how do we explain the occurrence of the rainbow in the context of light waves? How does it occur where it does? And the way to look at this is 42 degrees means from the eye of the camera, the photographer right here, if you made a cone from the eye going outward, the radius of that cone would be 42 degrees. The rainbow is not just fixed somewhere in space. It's with reference to the droplets in the air and where the person's eye is. And 50 degrees mean you make that cone a little bit wider and you see this other cone. And if you'll notice in the picture, it goes from red to purple as we know rainbows, but then the outer one, if you look closely, the colors are actually reversed. So the reason that we have rainbows and color forming, the colors are caused by different frequencies of light traveling at slightly different speeds in water. So here's a rain droplet, and this causes them to refract at slightly different angles, meaning it encounters the surface between water and air, and the reds and the blues bend slightly differently. So the blues at higher frequencies travel slower in water than the reds and are therefore refracted more. And as you come out, these different wavelengths are bent slightly differently. And what started as a combination of white light made up of all the colors comes out as colors that have been split, making a rainbow. And that angle, 42 degrees, is what determines the cone seen from the viewer going out to the arc of the rainbow. This slightly more complicated diagram with the viewer sitting here showing the primary rainbow and the colors, the reds and the purples coming in at slightly smaller angles. It also shows that the secondary rainbow is caused by light coming in, refracting and bouncing not once, but twice before coming out. So the second bounce inside the droplet gives us this secondary rainbow. Presumably, there's a third rainbow, but probably be difficult to see that kind of intensity. Another example of color in nature would be the Aurora Borealis, and this is a photograph taken under a bright full moon that's illuminating this massive ancient gold dredge that's stuck in place, probably from the 1930s or 40s, out at Chattanooga in central Alaska. You can see the moon lighting in the foreground and a beautiful aurora in the night sky. And we'll note that that color is exhibiting the common greens that are typical of aurora. So we don't have to understand how that color forms, but that's the excuse here. If we look down at the bottom here in this picture, this is shown the ground level and showing kind of a picture of how the aurora forms. It is caused by the interaction of solar particles and the interaction between electrons and oxygen, atomic oxygen, high between 100 and 400 kilometers above us. And depending on the chemical process going on between the electrons and the oxygen, as electrons are excited and de-excited, light can be emitted, and this is showing the green light at 557.7 nanometers is associated with oxygen. There are other colors, red light associated with nitrogen. You can get different colors, but this is the most common one. So the green light in the sky can be depicted in terms of wavelength, or if we can turn this into frequency, as we'll see next. So here's the visible spectrum, the colors we can see, part of the electromagnetic spectrum, but what we're looking at, the numbers here are showing the wavelength associated with different colors. So if we look here, similar to what we did for sound, we have wavelengths labeled in nanometers, 380 to 750 nanometers, so that's 10 to the minus 9th meters. We have the speed of light, which is 3 times 10 to the 8th meters per second. And we can, since we're talking about frequencies, we can calculate the frequency by dividing the speed by the wavelength. And if we do that, we get 4 to 8 times 10 to the 14th hertz. And if we write that a terahertz, meaning 10 to the 12th hertz, we could write this as 400 to 800 terahertz. So the violet here down would be 800 terahertz, the highest frequency, and the red at 400 terahertz. The visible spectrum is just one part of the electromagnetic spectrum. So here's the 7 and 4 times 10 to the 14th hertz. But then there's all these other familiar waves we've heard of: infrared, microwaves, radio waves, ultraviolet, X-rays, gamma waves. So the electromagnetic spectrum has this wide range of frequencies, and light was being provided as an example where frequency is the way to characterize certain kinds of color, just like frequency would be the way to categorize other kinds: radio waves, infrared, X-rays, and so on. So a signal can be examined for its variations in time or its variations in frequency. We looked at the ground motion before. We were looking at how a signal varies in time. And we're now going to see how a complementary and often more powerful way to look at signals is by examining how much content is stored at each frequency in a signal. So this shows the two perspectives of looking at three signals in time. When they sum together, they look like the red signal, but they're actually harmonic signals of constant value at three distinct frequencies. So this perspective is the time domain view, and this one, very different with just three spikes, is the frequency domain view. I would probably argue for this particular signal that the frequency domain is giving you a more complete, succinct picture of the signal. So here's an example to describe time series and frequency domain. Here is a time on one axis, temperature on the other. And we're used to the idea that there may be temperature may vary with what appears to be different scales of variation. We can take this signal and break it down into three parts: a low amplitude, high frequency oscillation, a low amplitude, long wavelength change, and then this dominant in between oscillation that taken together, we sum these together and we might see something like this. In the frequency domain, we see that this is represented by just three spikes. So here's the high frequency spike associated with the high frequency, low amplitude oscillation. The dominant signal is somewhere in between with the highest amplitude. And then the low frequency is shown here with some amplitude in between. So this signal right here could be represented in the time domain as shown here, or shown in the time domain, but represented by its parts shown here, or as spikes in the frequency domain. Here's a real recording of temperature over a 6-year period to show what real data look like. And you can see from this signal there's this brushy kind of oscillation, and there's also this dominant up and down signal. If you look in the frequency domain shown on the right, we can see a very different picture of the signal. The left and the right, they look very different. So one point is that time domain and frequency domain are radically different ways of looking at things. And in this case, we see that the x-axis is in terms of frequencies. And we can, if we take 1 over the value and get a period, we can see what the period of oscillation is for these spikes. And here's a 1-year peak. Well, 1 year, what might be causing a 1-year oscillation in temperature data? Or here's 1 day. So, here's the peak associated with the seasons. We revolve around the sun. And here's the one of night and day. We rotate. So there are other spikes in here, but as you would expect, you have a daily signal, and you also have an annual signal. So that introduces this idea of time and frequency domain and how it might be useful. So the signals we are interested in are ground motion. This could be described as displacement, velocity, or acceleration. So here's an example: ground motion in the time domain. And this is an exceptional period of time because it's a 10-day window. So this is in seconds on the x-axis, 10 to the 5th seconds. So there's about 10 days worth of time shown here, 8.6 times 10 to the 5th. And what you're seeing is an earthquake recorded, a magnitude 9 earthquake recorded in Canberra, Australia. This is from 2004. And we'll look at first here the time domain. You can see that the amplitude is dominated by the direct arrival of this earthquake wave. There's some other smaller signals in here, probably aftershocks that are also picked up. Now let's look at the frequency domain. So again, two radically different pictures of this event: time domain, frequency domain. What's shown here is frequency in hertz on the x-axis, and on the y-axis is the spectral acceleration. So it's the acceleration amplitude. What I flagged here are a couple things to keep your eye on. First of all, this is a seismometer, and the two peaks at the lowest frequencies, one is associated with 24 hours, the other is associated with 12 hours. So first of all, the seismometer can record the very slow oscillations of the earth due to the tides. It's the solid earth changing. So around this high quality seismometer, the earth is gradually changing according to the influences, the tidal influences from the moon and the sun that act upon the ocean and also the solid earth. So that in itself is amazing. The seismometer aimed at recording earthquakes can record periods of 24 hours and 12 hours. The next window looking in here is between 0.2 and 5 millihertz, and you see all these spikes in here. You see all the way out here at the high end is 0.5 hertz. So the instrument is recording things from frequencies of 0.5 hertz, which is a period of 2 seconds, 1, 2, 1, 2, all the way out to periods of 24 hours. So in there is all kinds of amazing things about this earthquake. Here we zoom in between those red bars, 0.2 and 5 millihertz. And this is showing you in the frequency domain, the ground motion at Canberra, Australia from this earthquake. And you see a remarkable picture of extremely sharp spikes shown here. So we saw nothing like this in the time domain, but in the frequency domain, we see a picture that tells us this ground motion is made up of all kinds of notes. You could call them like tuning forks, each one getting hit at a different frequency. It's a chord, a beautiful chord from the earth being played. Of course, we can't hear this, but the motion is telling us there are discrete frequencies in this signal. And what you're looking at is actually that the earth truly can ring like a bell. And you're looking at allowable frequencies, and the corresponding oscillation patterns of the earth are determined by the inner structure of the earth. What you're showing here is if you zoom in on the lowest end, 0.2 to 1 millihertz, here's a paper for this exact same seismic station and recording published in Science magazine in 2005. And the authors have labeled the type of oscillation and the period associated with each of these spikes. That this one is called the football mode. It's going in and out like a football. Or this is called the breathing mode, where it's just going, whole thing going out and in at a period of 20 minutes, 20 minutes to go out and back in. So this is a stunning view that for the biggest earthquakes, the earthquake rings like a bell, and the frequency domain is truly the way to look at this kind of ground motion. So it's useful to look at ground motion in the frequency domain. Let's go back to those recordings from Minto Flats, Central Alaska. Here we saw there were these oscillations with a period of about 6 seconds. I was labeled as this second signal we saw. Here's one of these periods. Here's another one right here. They both have this background 6-second period. So what's going on there? Now we're looking in the time domain. Well, we're going to go back a step to think about how oceans have generated microseisms, meaning the oceans around the world are the source of the main background excitation seen on seismometers everywhere. And so here's a 1951 paper by Bino Gutenberg from Caltech saying, as soon as fairly sensitive seismographs were available, it was found that the ground is never at rest. Really interesting statement, kind of the fact that we're presenting here. Gutenberg then says, actually, 1906, a German named Hecker published a paper on the origins of microseismic motion. In the following specific relationships between microseismic movement and various meteorological factors will be shown. The utilized materials are observations of horizontal pendulum motion in Potsdam from 1904 to 1905. So scientists for 100 years and more have known that the ocean generates signals that are recorded everywhere. No matter, you cannot get away from the oceans if you're a seismometer. So we'll see where this comes into Alaska. This is from Gutenberg's 1951 paper looking at different periods, so different bands of ground motion, and trying to understand hypothetical causes. Where is this coming from? Is it from close? Is it from far away? And one of the themes here is that you can record a seismogram of an event from right on top being a moose or an earthquake on the other side of the planet. The same is true for sources of noise. Where are these coming from? Could be right next to the seismic station, or it could be far away. And so Gutenberg's trying to break these down, looking at, in particular, even has these two bands, this 2 to 6 seconds and 4 to 10 seconds, ocean waves and hurricanes for the shorter periods, and then just the surf driven by wind against steep coast. Like if you stand at the beach and see sort of 10 to 15-second waves coming in, there is a certain period of those waves, and we'll see where those appear on seismometers. So here's a picture in the frequency domain of standard kind of background ambient motion. It's showing you a characteristic profile. Shown below is sort of a low noise level average all over the planet, from low frequency to high frequency. And we see this triangle peak here. And this top one shows kind of an average of high noise levels across the world. And you also see this peak right here. The blue rectangle is bounding between two frequencies. One is here, shown here at about 0.065 hertz or 15 seconds. And the other one is about at 0.2 hertz or 5 seconds. It turns out that both of these are associated with ocean-generated signals. We're looking at a station Manly in central Alaska, shown in black here, also another station nearby shown in red, but the noise level at this station in central Alaska fits in between these global lows and highs, with a peak here and a shoulder peak at this lower frequency. Turns out this lower frequency is the ocean waves, standard waves that you would see in the ocean coupling down into the seafloor. And the second frequency at higher frequency and much higher amplitude is caused by ocean waves interacting with each other and exciting the underlying seafloor. So the waves recorded by the seismometer are waves that travel in the solid earth, but they're originating from excitation from oceanic waves on the solid earth. I'll show a study from 2009 that looks at the connection between oceanic waves and global recordings of seismic noise. In some sense, this background material is not unique at all to Alaska, so I want to show that. In this study, they looked at a number of stations globally, but in the next slide, we'll be looking at three: one in France, ECH, one in Costa Rica, HDC, at mid-latitude or equatorial latitude, and one at southern latitudes, Kerguelen Island, PAF. So high latitude, middle, and low. This is a complicated plot, but it's worth spending some time on it. What we're looking at, first of all, on the right is averaged over the planet significant wave heights as a function of day and latitude. So the color means that there is high significant wave height. So it's from real data. What you see is that in the southern hemisphere, during the middle of the year, which for us in the north, this would be our summertime and their wintertime, there's very strong, significant wave height. Think about storms between Antarctica and the Southern Ocean. It's very strong in the red. In the northern hemisphere, during the winter time, which be the January, February, March for us, and then sort of October, November, December, you see the reds here. So the storms the significant waves are generated in winter events. It's in the southern hemisphere during the middle parts of the year, in the northern hemisphere during our winters. If we look at now seismic recordings at these stations, you see a similar kind of hourglass pattern. In France, The noise is strongest in the January, February, March, and at the end of the year, basically during the Northern Hemisphere winter. In the Southern Hemisphere, PAF, it's heightened. You can't see it that well, but the reddest reds are occurring right in the center of the year here. It's strongest associated with the reds shown here. And in the equatorial region, the sort of simple model is that they're seeing storms from north and south at all times of the year, and it kind of all balances out. So the kind of noise you see in this microseism period range of a few seconds, it all depends on what time of year it is. It doesn't depend on how close you are to the ocean. It depends on whether it's in whether you're in the middle of the year or the ends. At the same time as Gutenberg, there was a seminal paper in 1950 by Longate-Higgins who laid out the theory that says that when you have two ocean waves interacting, you can get this doubling frequency that excites the seafloor, a pressure wave that travels downward and excites the seafloor. So there were observations, and then there was the theory at about the same time. Fast forward 58 years, and lo and behold, Longate-Higgins is a co-author 58 years later, his seminal paper on a titled, same journal, Proceedings of the Royal Society, The Origin of Deep Ocean Microseisms in the North Atlantic Ocean. It took a long time to make a compelling link between the signals picked up by seismometers and exactly where in the world they were coming from, what kinds of storms. And this shows a figure from that paper looking at a few seismic stations shown here. They looked at a lot of stations from continental interiors, but these ones, they're trying to tie the link between the storm in the ocean and the seismic recording on land. And so what this is showing is black is the measured ground motion, and red is the modeled ground motion based on observed oceanic wave heights. So again, we're looking at a connection between modeled in red and recorded in black, and they're not in perfect agreement, but if you look at all these different seismic stations, you can see a strong correspondence suggesting that the source of the noise at these stations in continental North America, much of what that signal is caused by is related to observed oceanic wave heights. So this connection makes the link between the source of this solid Earth noise signal and the excitation in the ocean, first proposed in 1950. As the author says, establishes that deep ocean wave-wave interactions in the North Atlantic generate sufficient energy to account for the observed seismic amplitudes. So what's being recorded in Minto Flats? We've seen the first one was the moose signal. We've now seen that the oscillation with a period of about 6 seconds is related to distant oceanic waves exciting the seafloor. That's not unique to Minto Flats, just showing what the source of that noise is. We had the abrupt signal that decays with time. That was an earthquake from the far side of the planet. I failed to add that those waves are going through the core of the Earth, the iron core, to get to Minto Flats on the other side. And the last one, which you haven't covered, is this high frequency brushy signal, which I'm saying is caused by water and sediment transport in the Tanana River. And for that, please stay tuned for part B, the next video in the sequence, to see more on that. I'll finish with a quote. This is Bino Gutenberg, seismologist, standing here next to the old paper drums. And he concludes this seminal 1958 study. When the author started his research on microseisms 50 years ago, their causes and their theory were a source of extensive controversial discussions. It is still so today, 1958. More and more mechanisms have been considered for the generation of microseismic waves in the Earth's crust, and the theoretical problems of their propagation through the crust have multiplied with the development of the theory of elastic waves in layered media, and with the finding of wave times which had not been suspected in the earlier research. And this rings true today, decades later, that we're still trying to pull out all the details of exactly what is being recorded by seismometers. Suffice to say, things can come from locally like a moose and from the other side of the planet. And that remarkable instrument is what makes it so challenging to pull out all these pieces in a given seismic recording. Takeaway topics: a seismometer can record signals coming from close, like a moose walking next to it, and from far, like an earthquake on the other side of the planet. 2, the Earth is continuously in motion. This continuous motion, or ambient noise, provides information on many things besides earthquakes. That'll get covered in the next video. The frequency domain offers a powerful tool for analyzing signals of ground motion. The dominant signal of ambient noise, periods 5 to 8 seconds, is generated from the seafloor by the interaction of oceanic waves. And so please continue to the next YouTube video in the playlist, part B for this science fact, to see what this background in part A was preparing you for. Thank you for watching. Stick around for supplemental material.